For example, one method of doing line search is starting from any point. First of all, look if I'm going towards the left or the right, based on just the sign of the derivative. If the derivative here being positive, I just make sure I am going towards the negative direction. And then the line search actually performs a search. What is a search? A search, like a search in a computational algorithm, basically evaluates the objective function at multiple points and figure out which one has the lowest objective function. And in case of optimization, we usually don't perform a linear search. We actually perform a exponentially spaced search, right? So basically, I can start from a step. Maybe the step is initialized to be random, and if I already have some experience doing this optimization problem, I can start the step as the step where I find it to be the best last time around. Okay, so there are several possibilities. One possibility is that the step actually decreases the objective function. The other possibility is maybe my step is too large. I'm computing this point, which my objective function is actually higher. So if my objective function is actually higher, that means I have overshot, right? Because by definition of the derivative, I have taken to the right direction to know that I'm going to decrease the objective function if I'm taking the step to be small enough. So if my step is too large, that means I need to shrink my step size. If, on the other hand, if I'm taking a step size to be so small that my objective function might decrease, so first of all, I get a decrease. And two is that my decrease is actually very consistent with the gradient. What does that mean? Yes, question?
Just concerning the steps, you were saying that we're using exponential step and not linear. Doesn't that increase the possibility of overshooting because it might increase the steps a bit more?
Right. So it's actually I wouldn't say increases. So we ultimately want to get to a point that we know we are overshooting, because otherwise you don't know if my step size is too large. Right. So as long as I'm not overshooting, I want to actually take as large step as I want. Do you agree?
Sure. So that's one advantage over linear, is like being able to have larger steps.
Yeah, being able to get to the point that I overshoot faster is actually an advantage of this exponentially scaling or exponentially shrinking step size. Right. So if I'm stepping too small, I actually want to get to the point I overshoot as fast as possible. On the other hand, if my step size is way too large, let's say 1,000,000 times too large, then I don't want to take forever to shrink to the correct size, right? So again, exponentially scaling back. For example, dividing the step size by a factor of 2 if I'm too large, or multiplying the step size by a factor of 2 if I know I'm too small is probably the best way to do. Okay, and only when at a certain point, if the function is extremely well behaved, when I have a step size s being too small, step size 2s being too large, then I start to do linear search in between the known upper bound and known lower bound. All right, so that's the usual algorithm for line search, and there are several empirical criterions for when do you stop the line search. Like, what do you count as too large? What do you count as too small? And usually being too large means the objective function has increased, or the objective function has decreased by such small value that you know you are almost on the other side of the valley as high as you are. Okay, so that's overshooting. Undershooting means you are so small that the difference you get is exactly consistent with the derivative. So you are taking as small that step as as by the definition of your derivative. So line search basically goes back and forth between these too small and too large. So too small means your dj ds minus your delta j over delta s, right? usually divided by the magnitude of dj ds is less than a certain threshold, epsilon 0.1 or something. Too large, it can mean just your dj delta j over delta s. So over your dj ds magnitude is actually smaller than another epsilon, right? So this can easily count for your step size being too large or too small, right? Okay, any questions on the line search algorithm?
Yeah, sorry, what's the difference between dj and delta j? What are you defining the step size? So dj is the derivative in controls.
Okay, so delta j, yeah, the dj ds is the derivative. Delta j is the actual change in the objective function, and the delta s is the actual change in the design parameter. So you have stepped over delta s, and you find your objective function to have changed by delta j, right? So this being too small means the finite difference is very close to the derivative, while this being too small means the finite difference is actually much smaller than finite difference. Actually, it's a little bit different. Let me see. I have to actually take the. Oh no, this is false. So I have to take the sign of dj ds multiplied with this to be less than epsilon, because in case when delta j over delta s have a different sign as dj ds, which means when I take the sign over here, the whole thing is negative. That obviously means I have overshot, right? Which means the gradient tells me going this direction is going to decrease. When I actually take the step, I actually increase the objective function. That means I have stepped for too large. All right. So that's line search. Any questions so far on this? And on the if you go over the references and the Wikipedia, you can find all kinds of criterions, Goldstein criterion, and other very similar criterions to help you decide if you have stepped for too small or too large.